This stick figure is about to kick a ball, and at that time we start a stopwatch. Is there a relation between the time after the kick and the height of the ball? Yes, there is. But how do we go about explaining this relation? Graphing the height of the ball against time in a coordinate system is always a good start. Projectile motion has the shape of a parabola. This equation relates the height of the ball to the time after the kick, and it also happens to be a function. Functions are monsters that eat a number x and poops out a number y. Don't worry, they're really not that scary once you get to know them. I assume most of you are familiar with the real number line. On this line, every real number is represented. For example, 3 is here and -2 is here. The coordinate system is a rather ingenious invention to visualize relations between two variables. Consider the following simple relation between the two variables x and y. X is the length from A to B, and y is the length from C to D, and is equal to times x, twice as long as AB. Y equals 2x is an equation with two variables, and is the relation between x and y. Here, x is 2 and y is 4, which gives rise to the ordered number pair 2, 4. We can illustrate the relation by moving the point B along this number line. The position of the point D depends on the point B such that it is always double that of B. So if we move B to 5, then D must be at 10, as we see on the second pair of number lines here. And this gives rise to the number pair 5, 10. For a simple relation like this one, y equals 2x, this picture works just fine. For more complicated relations, however, this visualization isn't very useful. But see what happens if we take the second number line and place it vertically. Now the two number lines span a number plane, and they intersect at their zeros, known as the origin. The two number lines at a 90-degree angle, like these, and intersecting at their zeros, is called a coordinate system, or the Cartesian plane after its inventor, René Descartes. Any point on this plane is given by the perpendicular distance x to the vertical axis and the perpendicular distance y to the horizontal axis. Take, for example, the number pair 2, 4, the x and y from the first situation over here. This P1 is the graph or point of the number pair, and it's located with the perpendicular distance 2 to the vertical axis and the perpendicular distance 4 to the horizontal axis. The relation y equals 2x then is represented by this line, which comes about if we let a point trace a path as b moves along the horizontal axis. The path is the graph or the plot of the relation y equals 2x. The point P1 is the graph of the number pair 2, 4, and the point P2 of 5, 10. Though one is a point and another is a number pair, it is customary to stress their association by referring to the point as, for example, P2, 5, 10. Good. Let's put this to use. We've come across equations with two variables, such as this one. In this equation, x and y are variables, placeholders for any number. And seeing as this is an equation, we might go about looking for its solution. Issue is that there is no one solution to an equation like this one. We would need two coupled or simultaneous equations with two unknowns x and y in order to find a solution here. I covered that in depth in a video you can find here. Therefore, with only one equation and two variables in it, there are many solutions to it, and a solution is a pair of numbers that together make the equation true. With x equal 1 and y equal 3, the equation 9x plus 2y equals 15 is a true statement. This pair of numbers, or the ordered number pair 1, 3, is a solution to the equation. The number pair -2, 6, however, isn't a solution. Writing this calculation, remember the parentheses around -2. This equation says that -6 equals 15, which is false, and the number pair -2, 6 is not a solution. Here's a list of some other solutions. The number pairs -1, 12, 3, -6, and 5, -15 are also solutions because when substituted into the equation, they make the equation true, which is checked here just to be sure. A relation is any set of points in a coordinate system. Here I've graphed the solutions of the equation we found so far. The equation then is a relation between x and y. The process of finding solutions is called solving the equation, and I won't list any more because there are infinitely many. The line in the coordinate system is the graph of the equation and consists of all the points that are the graphs of the solutions of the equation. Lines, or indeed any curves in a coordinate system, can be regarded as a set of really closely spaced points and are therefore relations also. In summary, we could expand the header here with the word or and the letter S. The point of this being that equations of two variables are relations. Functions are monsters. They eat a number and poops out a number. This monster is a double-up monster. When it eats a 1, it poops out a number 2. Or when we feed it a -4, it poops out a -8. This scary monster multiplies by 3 and adds 1. When we feed it a 2, it multiplies by 3 and adds 1, which equates to 7. Or when it eats a -5, it poops out a -14. If we let x represent the number that the monsters eat and y the poop, then they represent functions where y is a function of x. The double-up dragon is a function y equals 2x, which we encountered earlier. And this thing is a y equals 3x plus 1 function. These two variable equations are relations between x and y, and also functions because only one poop is assigned to every food. There can be many foods that give the same poop, but not many poops to the same food. We say the functions are one-to-one or many-to-one, but not one-to-many. This Venn diagram illustrates that functions are a subset of all relations, and these are the requirements to be a function. In other words, a function is a special type of relation. Our definition: functions are relations which takes each x value to exactly one y value, meaning they can be one-to-one or many-to-one. Additionally, we also use a particular notation to indicate that a relation is a function, and it's called a functional notation. If we call this monster or function f and this g, then y is the function value for a particular value of x. F parentheses x reads f of x, and we might write y equals f of x because this is the f function, and y equals g of x because this is the g function. Using this notation, our first two double-up calculation can be written as follows. Omitting the y because f of x equals y, the calculations become f of 1 equals 2 times 1, where 1 is substituted for x, equals 2. And similarly for f of minus 4. In calculating the function value at minus 4, we need to remember this parentheses. These are the calculations for the g monster. Also here we have replaced x in the function such that g of 2 is equal to 3 times 2 with 2 for x plus 1, which is equal to 7. And similarly for g of negative 5. We can even omit the calculation and write it more compactly. That is, this calculation can be written as g of negative 5 is equal to negative 14. And similarly for the other function values we've calculated. You may come across the function value expressed as such, and here's a couple of ways to interpret it. It can be interpreted in a couple of different ways. The value of g at negative 5 is negative 14, or the point negative 5, negative 14 lies on the graph of g. It's going to take some practice getting used to this notation, but the hope is that after seeing it many times, it'll start to make sense. It can be useful to think of functions as so-called mappings, which takes a value from the domain to exactly one number in the range. The function value is an image of an x value, and an alternative way of expressing the function g of x equals 3x plus 1 is using arrow notation. This reads that g is a function such that x is converted to 3x plus 1. X represents a member of the domain and determines the value of only one member y in the range for g to be a function. Alright, let's leave this for now. I'm gonna talk more about the domain and range of functions in another video. And from now on, we're gonna stick with the functional notation. Finally, you may use whatever variable you wish to define a function. For example, p of t equals t squared minus 2t, where the function is called capital P and the variable is lowercase t. We've just covered the conditions for a relation to be a function. Let's bring that back up. There. Consider these two relations. Here are two relations and their graphs. A relation must pass a vertical line test in order to be a function. The relation is a function if each vertical line cuts the graph no more than once, and is not a function if any vertical line cuts the graph more than once. Of the two relations, x equal y squared is therefore not a function. There is a one-to-many relationship between x and y in this relation. Look at the vertical lines. Most places there are two y values for each x, like here and here. The other relation, y equals a half x minus 1, is, however, a function because it passes the vertical line test. The vertical lines only ever crosses the function's graph once. Consider a parabola. This graph is called a parabola and the function is y equals x squared. The only difference compared to the first relation is that y and x have switched places, and this results graphically in a rotated parabola, or more generally, a graph that is mirrored in the diagonal. This one is a function, however, because it passes the vertical line test. It seems a little strange that one is a function and the other isn't, because they are so similar. But the ability of a function to output one and only one value for each x, which we verify with the vertical line test, by the way, is crucial when putting this to practical use. Ask yourself the following question. Is there a relation between the temperature and the day of the year? Just colloquially speaking? Yes, right? How about the velocity of a car and its braking distance? Yes. And how about number of pets and hair color? No, those two are not related. We agree there is a relation between these different variables. But what if I asked, how do they relate? Now a simple yes or no won't do. A large part of mathematics deals with finding relations between variables. We can use the term variable about, for example, the temperature and the day of the year because we can assign a number to them. The word variable implies that it is not constant but can take on different values depending on various factors, such as changes over time, as is the example here, or it could be due to variations in any other related variables. Oftentimes, in scientific experiments and analysis, the designation of a dependent and independent variable arises naturally. Researchers manipulate or control one variable and observe its effects on another. The other variable is said to be dependent on the first, the independent variable. So, of the variables temperature, day of year, velocity, and braking distance, which are the dependent and independent variables? The temperature, which is assigned the variable T, depends on the day of the year, which is assigned the variable X. Temperature is the dependent variable and the day of the year is the independent variable. Braking distance D depends on the velocity V. Braking distance is dependent and the velocity is the independent variable. Could we assign variables to the last example here? Certainly, and actually the hair color is an interesting one, because we don't usually put a number on color. That doesn't mean we can't categorize people into different hair colors. Hair color then is a categorical variable, whereas the other variables are numerical variables. Consider the case here. A class in the subject physical education have been assigned the task of collecting data from the students in order to assess which factors, if any, such as lifestyle choices or physical attributes, contribute to a heightened or lowered cardiovascular endurance score. Cardiovascular endurance, commonly referred to as cardio, is scored on a scale from 1 to 10. Which variables should the students investigate? The students could look at cardio in relation to a lot of different factors that may or may not relate to the cardio score, such as muscular strength, agility, resting heart rate, flexibility, sleep duration, screen time, fruit and vegetable consumption, water intake, or many others. Let's consider here how cardio score relates to daily physical activity among these 7 students. For example, student number 1 has 40 minutes of daily physical activity and a cardio score of 6.5. Glancing at the numbers, it seems that the more daily physical activity of the student, the higher cardio score. Let's graph it. 2 things to make a note of here. If you plot a relation between 2 variables and the variables somehow represent a real-world quantity, then remember units on the axes. Typically, the independent variable goes on the x-axis and the dependent variable goes on the y-axis. The units are displayed on the axes. Minutes for the daily physical activity, but no units for the cardio score, as it is unitless, just a number between 1 and 10. The graph shows the same thing that we saw in the table, that more daily physical activity seems to correlate with a higher cardio score. And not only that, looking at it, it does seem like the points fall along a straight line. Let's find the line of best fit. Finding the line of best fit, as shown here, along with a function for that line, is called regression analysis and will be the topic of another video. The function allows us to make educated guesses about the values within the data range, something called interpolation, and even make predictions beyond it, extrapolation. However, we should be careful about which conclusions we draw from this. There's much to be said about the quality of the data and the model we've derived from it. This is more on the topic of statistics, actually. But it's not too far a stretch to say that the data suggests a linear relationship between the daily physical activity and cardio score among the students. Anyway, this discussion about the line of best fit is not where I'm going with this. The point I'm trying to make here is that we have 3 different representations of the same thing. The data presented in a table, on a graph, and by a formula, each of which are useful in their own right. It's these different representations I want to talk about next. Variable relationships can occur in 4 different forms: table, graph, formula, and language. Let's look at each representation, its strengths and weaknesses, and see how we can convert or switch between them. Let's first look at the language representation. The relationship is described by way of words and could go something like this. When you take a ride with the math cab, the starting price is $12, and for every kilometer you travel, they charge an additional $3. This is a description in words of a relationship between the distance traveled and the fare price. Could you work out the price of a 5-kilometer ride? A 5-kilometer trip is $27. From this description, we could even make a formula to calculate the fare price. Let's call the fare price P and the distance traveled D. Price depends on the distance according to the following function. By inserting a number for the distance, like 5 kilometers, into the function, we can calculate the fare price. We've converted a relationship in language form into a formula or function. The advantage of using language is that it is common to us all. You needn't prior knowledge of functional notation or anything of the sort to understand the description here. However, language will struggle as soon as the relations become more complex. But that's exactly where mathematical language comes in handy. To describe complicated relations is what math is there for, after all. Let's move on to a new representation of a variable relation, the formula representation. And the example describes a disease epidemic. The formula, which is also a function, the distinction between formula and function, again, having to do with whether the formula satisfies the requirements of being a function or not, it represents how many people are infected as a function of days after a disease outbreak. X represents the number of days and f of x the number of infected. That means we can, for example, calculate the number of people infected after 3 days by substituting 3 for x and calculating the function value. Therefore, after 3 days there are 440 infected. How many are infected on day 0? For this calculation, we don't need a calculator, because the result of any number raised to the 0th power is 1. Therefore, the outbreak started with 385 people. And this initial value just so happens to be the number right here in the function. Let's plot the function, the number of days x on the x-axis and the number of people infected f of x on the y-axis, while remembering to include units on the axis labels. The function here is an exponential function, a topic for another video. These types of functions encapsulates the cascading effects of an uncontrolled disease outbreak. Whereas the numbers don't look too scary in the beginning, it's the not too distant far end of this graph that spells doom and gloom. We've already pointed out that the initial value corresponds to this number in the function. And this number tells us that the number of infected people grows by 4.5% every day. Here then, we've converted the relationship from a formula into a graph. And a language explanation could go something like this. At the outbreak of this disease, 385 people are infected, and the number is growing by 4.5% every day. Let's look at a graphical representation. The graph shows the temperature variation during a spring day. The time of the day is on the x-axis and the temperature on the y-axis. X is used for time and T for temperature, and the units are hours and degrees Celsius. If we want to know the temperature at 6 o'clock in the morning, we can extract the coordinates. Remember that the point we're looking for has the perpendicular distance x of 6 to the vertical axis and the perpendicular distance y of, shall we say, 13.3 to the horizontal axis. We can read the point to one decimal place, but it's hard to be more precise than that when reading off of a graph like this one. I've extracted some more points. At noon, the temperature is 17.3 degrees. At 6 in the evening, it's 18.6 degrees. And at midnight, it's 14.0 degrees approximately. By extracting the points of the graph, we've converted the graph into table form. The exact data represented by the graph can only be approximated when visually interpreted as we're doing here. In other words, while graphs are fantastic visuals, some precision of the data is lost using this representation. There are many ways of describing a graph using language. If we look at the graph's trajectory, the temperature appears to be increasing for some time until about 17 o'clock, after which it decreases. It curves upwards until about noon, after which it starts to flatten out. Also, the graph exhibits its maximum around 17 o'clock and its minimum around 3. Here, I've used interval notation in describing the graph's monotonic relationship. The interval reads 3 to 17, and I've added that the graph is decreasing from 0 to 3 and 17 to 24. While it is increasing from 3 to 17, it has an upward curve from 3 to 12 and a downward curve from 12 to 17, meaning that it flattens out over that interval. We might use other terms like domain, range, extrema, and sign diagrams to further describe the trajectory. That's, however, beyond the scope of this video and will be covered in the next video on functions. The power of the language description is that it captures what is most important about the graph. Yes, some information is lost, but a language description pointing out the most important characteristics should accommodate any graph. The final representation is the table form. Some farmers have measured the effects of fertilizer on crop yields in a field with an area of 1 hectare or about 2.47 acres. This is how they relate. The amount of fertilizer used is measured in kilograms and the yields in tons. The data suggests that using more fertilizer leads to greater crop yields. Let's graph the number pairs. The graph with fertilizer in kilograms on the x-axis and crop yields in tons on the y-axis also suggests an upward trend in yields the more fertilizer is used. So we might proceed to find the line of best fit. This is the line of best fit, and this is its function. We could use the function to extrapolate on the data, and the trend continues with better yields the more fertilizer is used. But for how long will this trend continue? Will the fields have increased crop yields even when they are swimming in fertilizer? Well, no, right? Of course not. At some point, increasing the amount of fertilizer will start having diminishing returns. That is, there really isn't a so-called linear relationship between the amount of fertilizer used and crop yields, or at least not across all possible x values. While we have powerful tools to describe trends in datasets, we also need to be smart about how we use it. The relation might be displayed using a broken line graph. In a broken line graph, the points are connected with line segments which can help to see the trend over time. The line segments show that the first couple of points tend to fall on the same line, but perhaps we already see the trend starting to fall off towards the end here, since the slope of the last couple of line segments is slightly lower. Finding the optimum is going to be an ecological and economical assessment, which can be informed by this data. We have converted the table to a graph and at least attempted to describe it using a formula. Alright, this is the end of the video. I hope you now have an idea about what mathematical relations and functions are and why they're useful. I hope this video will motivate you to further explore the more theoretical aspects of this topic. Let me know in the comments if you want my next video to be in English as well. I have another video related to algebra planned that I want to finish first, but after that I want to make the follow-up to this one. Other than that, like, comment and subscribe, and thanks a lot for watching.